December 19th, 1944, Aromanches-les-Bains, Normandy coast, France. Oberst Friedrich von der Heide stood motionless on the wind-swept cliffs overlooking the English Channel, his hands gripping Zeiss binoculars that trembled slightly as he swept them methodically across the bay below. The cold December wind cut through his Wehrmacht greatcoat, but the 37-year-old veteran of Crete, North Africa, and the blood-soaked Eastern Front barely noticed the physical discomfort. He had witnessed countless feats of military engineering across 3 years of brutal warfare. Bridges built under fire, fortifications erected overnight, supply lines maintained through impossible terrain. But nothing in his extensive combat experience, nothing in his rigorous training at the Kriegsakademie in Berlin, absolutely nothing in the collective wisdom of German military doctrine had prepared him for what lay before him in the churning gray waters of the English Channel on this bitter winter morning. Das ist unmöglich, he whispered to his adjutant, Hauptmann Klaus Weber, who stood beside him with his own binoculars trained on the extraordinary scene below. This is impossible. They are building a harbor, not capturing one of our fortified ports, not establishing a temporary beachhead supply point, building an actual functioning harbor. From nothing, in the open sea. This cannot be real. But it was real. Devastatingly, undeniably, impossibly real. Below him, stretching nearly 2 miles into the channel from the quiet French coastal village of Aromanches, lay what Allied forces had designated Mulberry Harbor, B, a massive artificial port constructed entirely from prefabricated components manufactured in Britain, towed across 100 miles of submarine-infested waters, and assembled in just 12 days, while German artillery still ranged the beaches and Luftwaffe bombers attempted nightly raids. The harbor was operational, bustling with activity that mocked every assumption of German strategic planning. Von der Heide could see Liberty ships moored at floating pierheads, their cranes swinging cargo nets filled with supplies onto waiting trucks. He watched vehicles, American GMC trucks, British lorries, even tanks, driving down what appeared to be steel roadways that floated on the water's surface, rising and falling with the tide, yet remaining perfectly level and stable. He observed landing craft approaching protective breakwaters that reduced the channel's notorious waves to gentle swells, allowing smaller vessels to unload in conditions that would have made beach landings impossible. The statistics that von der Heide would later include in his detailed reconnaissance report were staggering and would fundamentally rewrite German understanding of Allied industrial capacity. The harbor incorporated 600,000 tons of concrete and steel, more material than Germany had used to construct the entire Atlantic Wall fortifications in the Pas-de-Calais region. It featured 33 separate jetties and pierheads, capable of accommodating ocean-going vessels up to 10,000 tons displacement. It included 10 miles of floating roadways that could support vehicles weighing up to 40 tons driving at normal road speeds across water that was 30 feet deep. It utilized 93 deliberately sunken ships, obsolete freighters and warships scuttled in precise patterns to create additional wave protection for the massive concrete breakwaters. Most devastatingly, from a German strategic perspective, it was handling a daily cargo capacity exceeding 9,000 tons, more tonnage per day than the ancient port of Cherbourg, which German forces had spent 4 years fortifying with concrete, steel, mines, and a garrison of 21,000 troops, could handle even in peacetime conditions, with all facilities intact and operational. Von der Heide had been sent to Normandy from his assignment with the 6th Parachute Regiment, specifically to assess the Allied supply situation, to identify vulnerabilities in their logistics chain, to find weak points that German forces might exploit to disrupt the endless flow of men and materiel, sustaining the Allied advance toward Germany's borders. He was supposed to report back to Field Marshal Gerd von Rundstedt's headquarters at Saint-Germain-en-Laye, with intelligence that would help German commanders plan counterattacks, position reserves, allocate scarce resources. Instead, he found himself witnessing what he would later describe in his classified report as the death of traditional military logistics doctrine and the birth of something that defies every principle we learned at Staff College. The Germans had gambled everything, their entire defensive strategy in Western Europe, the positioning of their forces, the allocation of their dwindling resources, on a strategic calculation that seemed unassailably logical. The calculation was simple, elegant, and apparently foolproof. The Allies would need a major deep-water port to sustain any invasion of France. Ports required specialized infrastructure: docks, cranes, warehouses, rail connections, protected anchorages that took decades or centuries to develop. Germany controlled every major port on the French coast from Dunkirk to Bordeaux. Therefore, deny the Allies access to these ports by fortifying them heavily and preparing to demolish facilities before capture. And any invasion would wither on the beaches within weeks, starved of the supplies necessary to sustain offensive operations. Deny them Cherbourg, with its massive harbor facilities, and the invaders would be limited to whatever supplies they could land directly on open beaches. A method that weather, tides, and simple mathematics would limit to perhaps 3,000 tons per day at best. Hold Calais and Boulogne, the closest major ports to England, and therefore the most logical invasion points, with sufficient forces to either repel landings or destroy port facilities if capture became inevitable. Fortify Le Havre, Dieppe, Saint-Malo, and every other coastal town with harbor facilities. Make the capture of each port so costly in time and casualties that by the time Allied forces finally secured functioning port facilities, the Wehrmacht would have reorganized its defenses, brought up reserves, and created defensive lines that would make further Allied advances prohibitively expensive. It was logical. It was based on sound military analysis. It was the strategy that German High Command had committed to, that Field Marshal Rommel had been sent to France to implement. It was completely, catastrophically, irrevocably wrong. What von der Heydt witnessed through his binoculars on that December morning was the physical manifestation of a fundamentally different approach to warfare, an American industrial philosophy that German planners had failed to understand, or even imagine was possible. The philosophy was startlingly simple. If you need something that doesn't exist, you don't waste months or years capturing and repairing something your enemy has built and will certainly try to destroy. You design what you need from first principles. You engineer solutions to whatever technical problems stand in your way. You mobilize your industrial capacity to manufacture the required components, and you assemble it on site under combat conditions if necessary. You manufacture the solution. You ship it across an ocean. You assemble it under fire. And you make it work, because failure is not an option. This was American warfare in its purest expression, the application of overwhelming industrial capacity, systematic engineering methodology, and ruthless pragmatism to military problems that conventional thinking considered insoluble. The very concept violated German military doctrine so fundamentally that many officers, even when shown photographs and detailed intelligence reports, simply refused to believe what they were seeing was real. It couldn't be real, because it couldn't be done. Therefore, the intelligence must be wrong. The photographs must be deceptive. The whole thing must be some kind of elaborate ruse. Except it wasn't. It was real. It was functional. And it was processing more cargo daily than many permanent ports that had taken centuries to develop. The story of Mulberry Harbor begins not with engineering genius, but with blood on the beaches of Dieppe, France, on August 19, 1942. Operation Jubilee, the ambitious raid on this heavily defended French port, would teach lessons about coastal assault that were written in the casualties of 6,000 men and could never have been learned through theoretical planning. At precisely 500 hours on that August morning, as dawn broke over the English Channel, 6,086 men approached the beaches of Dieppe in a fleet of landing craft, primarily Canadian troops from the 2nd Canadian Infantry Division, supported by British commandos, a small number of American Rangers, and units of the Free French Forces. The men had trained for months for this operation, practicing beach assaults, rehearsing tactics for urban combat, preparing to capture and hold the port facilities long enough to destroy German defenses and gather intelligence before withdrawing back across the channel. On paper, the plan appeared sound. Dieppe was defended by elements of the 302nd Infantry Division, a static defensive unit composed largely of older soldiers and those recovering from wounds sustained on the Eastern Front. Intelligence assessments suggested the defenses, while substantial, were not impregnable. The element of surprise would be crucial, but Allied planners believed it could be achieved. What those planners had not fully appreciated was the lethal efficiency of German coastal defenses when manned by even second-rate troops who had been given 2 full years to prepare their positions. The German defenders waited in concrete bunkers with walls 6 feet thick, impervious to anything except direct hits from the heaviest naval guns. Their machine guns, primarily MG-34 and MG-42 models, capable of firing 800 to 1,200 rounds per minute, were positioned with mathematical precision to create overlapping fields of fire that covered every meter of beach. Anti-tank obstacles fabricated from railway rails had been welded together and driven deep into the beach at the high water mark. Barbed wire entanglements stretched 40 feet deep in places. German engineers had demolished buildings along the waterfront that might provide cover, leaving clear fields of fire. They had positioned 37mm anti-tank guns to cover the single vehicle exit from the beach. When the Canadian forces hit the beaches at 5:20 hours, they discovered that courage, training, and determination meant nothing against mathematics and physics. The landing craft approached beaches composed of large stones rather than sand, stones that absorbed the tracks of Churchill tanks, preventing them from gaining traction. Tanks that managed to get off the landing craft immediately bogged down, became immobilized, and were systematically destroyed by German anti-tank guns firing at point-blank range. The infantry, emerging from their landing craft into a storm of machine gun fire, began dying before they could reach cover. The operation lasted 9 hours and 30 minutes. It was not merely a defeat, it was a catastrophe of almost unimaginable proportions. Of the 6,086 men who landed at Dieppe that morning, 3,623 were killed, wounded, or captured, a casualty rate of 59.6%. Nearly 6 out of every 10 men who went ashore became casualties. The 2nd Canadian Infantry Division effectively ceased to exist as a cohesive fighting unit. Not a single tank made it off the beach and into the town. Not a single German defensive position of any significance was destroyed. The port facilities remained completely intact and operational, untouched by Allied forces who never came close to reaching them. More importantly for future planning, the attempt to capture the port facilities had failed so utterly that even if the raid had somehow succeeded tactically, the Wehrmacht defenders would have had ample time to demolish every crane, every dock, every piece of infrastructure that made Dieppe function as a harbor. The Germans had prepared demolition charges on every critical piece of equipment. They had rehearsed destruction procedures. They had orders to deny the Allies use of the port by any means necessary. Lieutenant General Bernard Law Montgomery, reviewing the detailed after-action reports in September 1942, wrote a memorandum to Combined Operations Headquarters that summarized the lessons with brutal clarity. The Dieppe operation has demonstrated conclusively that direct assault on a defended port is not feasible with acceptable casualties. The Germans have had 2 years to fortify these positions. They have placed anti-tank guns to cover every possible exit. They have sighted machine guns in mutually supporting positions. They have registered their artillery on every approach route. Even if we succeed in landing tanks, the only exits from most beaches are easily blocked. The conclusion is inescapable. We cannot capture ports by frontal assault. If Operation Overlord requires port facilities to sustain operations, and we know it does, then we must provide those ports by other means. This brutally honest assessment reached Combined Operations Headquarters in London in October 1942, where it was reviewed by Vice Admiral Lord Louis Mountbatten, Chief of Combined Operations. Mountbatten understood that Montgomery's assessment was not defeatism, but simple military reality, based on empirical evidence purchased at the cost of thousands of lives. He had already been wrestling with the logistics problem that threatened to make any cross-channel invasion impossible before it even began. The mathematics of the problem were unforgiving. An infantry division in active combat required 600 to 700 tons of supplies daily. An armored division consumed even more, up to 800 tons daily, with fuel consumption alone accounting for 300 tons when actively engaged. Operation Overlord, in its initial planning stages, called for landing 6 divisions on D-Day, building to 18 divisions by D+14, and ultimately deploying 60 divisions by D+90. The supply requirements: D-Day with 6 divisions required 3,900 tons daily. D+14 with 18 divisions required 11,700 tons daily. D+90 with 60 divisions required 39,000 tons daily. These figures assumed relatively static divisions. Active combat operations could double or triple consumption. Conventional military wisdom dictated one solution: capture a major port on D-Day or immediately thereafter. But Dieppe had demonstrated the utter futility of that approach. Every major port on the French coast had been transformed into a fortress. Cherbourg had been turned into a citadel, with 21 major coastal batteries, 47 concrete bunkers, over 30,000 mines, and prepared demolition charges on every piece of port infrastructure. A garrison of 21,000 troops under Major General von Schlieben had orders to defend to the last man, then destroy everything. Allied intelligence estimates projected that even if Cherbourg could be captured quickly, which seemed unlikely given Dieppe's lessons, German demolitions would be so thorough that repairs would require 3 to 6 months before the port could handle adequate cargo. Royal Navy planners calculated that beach landing capacity topped out at 2,500 to 3,000 tons per day under ideal conditions. This was less than 1/3 of minimum requirements for the initial invasion force, less than 1/10 of what would be needed by D+90. The logistical impossibility threatened to kill Operation Overlord before a single soldier set foot in France. Into this seemingly insoluble crisis stepped Commodore John Hughes Hallett, naval advisor to combined operations, who had witnessed the Dieppe disaster firsthand. In a planning conference in October 1942, Hughes Hallett made a suggestion greeted with stunned silence. "Gentlemen, we have established that we cannot capture ports. We have also established that we cannot invade without ports. If we cannot capture ports and we cannot invade without ports, then there is only one logical solution. We must bring the ports with us." The concept of artificial harbors was not entirely new. During World War I, British engineers had experimented with floating piers for the Dardanelles campaign, achieving limited success with small-scale installations. Winston Churchill, who had served as First Lord of the Admiralty during Gallipoli, had never forgotten those experimental floating piers. In May 1942, months before Dieppe, Churchill sent a brief memorandum to Mountbatten. "Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves." This 48-word memo would ultimately mobilize 45,000 workers, consume resources equivalent to building 6 battleships, and create structures that German intelligence would classify as impossible, even when photographs proved their existence. The initial concept was deceptively simple. Construct floating piers that rise and fall with tides, connect them to shore via flexible roadways, protect the installation from waves with breakwaters, and create a system that could be manufactured in Britain, transported across the Channel, and assembled off the invasion beaches. But translating this vision into reality at the scale required for Overlord revealed engineering challenges that seemed insurmountable. The English Channel was notorious for conditions that destroyed conventional harbor facilities. Tidal ranges averaging 18 feet, reaching 23 feet during spring tides. Wave heights during storms exceeding 8 feet, reaching 12 feet during major systems. Current velocities during tidal changes of 3 to 4 knots. Water depths varying from 20 to 40 feet 1,000 yards offshore. Winter storms with winds exceeding 60 miles per hour. Naval architects at the Admiralty formed 3 study groups in May 1942 to evaluate feasibility. Their findings in July were unanimous in pessimism. The structures would be the largest floating objects ever built. Steel and concrete requirements would strain British industrial capacity. The timeline, years, made it impractical before 1945. Then came Dieppe. The casualties transformed artificial harbors from interesting theory to absolute necessity. In September 1942, the War Cabinet authorized unlimited resources for the Artificial Harbor Project, soon codenamed Mulberry. Budget, whatever necessary. Priority, equal to bomber production. Deadline, June 1944, 21 months away. Between September and November 1942, 17 engineering firms submitted proposals. Designs ranged from conservative modifications of floating dock technology to radical concepts bordering on science fiction. The winning proposal came from Harold Wills and Alan Beckett, combining multiple proven technologies. Massive concrete caissons floated to Normandy, then sunk as breakwaters. Floating, steel pontoons for piers with flexible joints. Steel roadways on floating pontoons, allowing vehicles to drive from ships to shore. Block ships, obsolete vessels scuttled as additional wave protection. The concrete caissons, designated Phoenix, represented the greatest challenge. Specifications: 200 feet long, 60 feet wide, 60 feet tall, weighing 6,000 tons when ballasted. They would be hollow, floating during towing with shallow draft, then deliberately flooded to sink in controlled fashion to the seabed. Each would displace tonnage comparable to cruisers, the largest concrete structures ever transported by sea. To make such enormous structures strong enough to survive towing, deliberate sinking, and years of wave action required advances in concrete engineering at the edge of 1940s capability. Engineers at the Building Research Station in Watford spent 3 months testing concrete formulations. The mixture they developed: Portland cement from expanded production facilities, aggregate from carefully selected quarries, seawater for mixing, controversial but testing proved it worked, chemical, admixtures to accelerate setting. Steel reinforcement required 350 tons per caisson, arranged in complex 3-dimensional matrices. The calculations were performed by teams of human computers, predominantly women with mathematics training, working with slide rules and mechanical calculators, solving thousands of differential equations describing force distribution. The ballasting system allowing controlled sinking presented another challenge. Each caisson contained 12 separate compartments flooded individually. Sequence and timing had to be calculated precisely. Flood all simultaneously, and the caisson might sink too quickly and crack. Wrong sequence and it might tilt. Too slow, and it might drift off position. Naval architects developed procedures specifying exactly which valves opened, in what sequence, with exact timing. They tested scale models in wave tanks until procedures resulted in models sinking vertically and settling upright within inches of targets. The floating roadways, designated whale pontoons, presented different challenges. These needed to rise and fall 20 feet with tides while maintaining level surfaces, flex with waves without breaking, support 40-ton vehicles, stretch up to 1,000 yards, withstand channel storms. The solution: articulated steel pontoons 80 feet long and 25 feet wide, connected by universal joints allowing 15 degrees rotation in any direction. Each pontoon was a hollow steel box with enough buoyancy to support maximum loads with 12 inches freeboard. The universal joints were mechanical masterpieces, ball and socket arrangements where 18-inch diameter steel balls on one pontoon fit into matching sockets on adjacent pontoons, with mechanical locks preventing separation while allowing rotation. The joints had to transmit 50-ton vertical loads while accommodating angular movement, be rapidly installable, and withstand repeated stress cycles. Manufacturing required precision machining, normally reserved for naval gun turrets. The anchoring system, the spud legs, solved the traditional anchor problem. Each pontoon had 4 telescoping steel legs, 40-foot pipes sliding within sleeves welded to the pontoon underside. The legs extended to the seabed, allowing roadways to rise and fall with tides while leg tips remained planted. Massive triangular steel feet spread loads over 9 square feet, preventing sinking or slipping. Testing in the Solent revealed problems. Legs walked across seabed during storms. Larger feet solved this, increasing bearing area and preventing drift. By June 1943, major engineering problems were solved on paper and in prototypes. Phoenix caissons could be built with adequate strength. Whale pontoons could be manufactured using standard shipyard techniques. Spud anchoring would hold position through storms. Universal joints would allow flexibility while transmitting loads. Ballasting systems would enable controlled sinking to precise positions. But solving engineering problems was the easy part. Now came the truly difficult challenge, actually manufacturing 146 Phoenix caissons, weighing 6,000 tons each, hundreds of whale pontoon sections, and thousands of tons of additional components, all within 12 months, using an industrial base already fully mobilized. The Mulberry production program, when fully mobilized in mid-1943, dwarfed any civilian construction project in British history. To construct 146 Phoenix caissons required more concrete than Britain used for all civilian construction in 1938, poured in 14 months. The Ministry of Works identified construction sites meeting stringent requirements: proximity to deep water, access to rail lines, available labor, protection from bombing, adequate space for multiple simultaneous builds. Major sites established at 6 locations: Marchwood, near Southampton, 28 caissons, built in massive concrete basins excavated from reclaimed marshland. Stokes Bay, near Gosport, 31 caissons, using pre-existing dry dock facilities. Thames Estuary, 22 caissons, where shipyards converted from ship construction. Richborough in Kent, 37 caissons, in a purpose-built 800-foot basin. Smaller sites at Portsmouth, Portland, and other South Coast locations, 6 to 14 caissons each. Each major site operated 24/7 in 3 8-hour shifts, maintaining continuous production from June 1943 through May 1944. The workforce totaled 20,000 at peak production, including skilled concrete finishers relocated from civilian projects, steel fixers installing 350 tons of reinforcement per caisson, carpenters building wooden forms requiring precision within 1 inch over 200 feet, crane operators managing lifting equipment, general laborers performing countless support tasks. The workforce composition revealed Total War's transformation of British society. Approximately 40% of concrete workers were women who had never worked construction before 1942. They mixed concrete, operated equipment, finished surfaces, and performed work pre-war society considered exclusively male. Dorothy Richardson, 23-year-old former shopkeeper from Plymouth, worked at Marchwood, April 1943 through May 1944. In a 1987 interview, "We poured concrete from first light to full dark. The forms were 60 feet tall. We needed scaffolding to reach the top. My job was surface finishing with long-handled floats. It was exhausting. My shoulders ached every night, but we knew those concrete boxes would protect our boys when they landed in France. That knowledge kept us working when we could barely stand." The 13-day construction cycle per caisson. Days 1 to 3, excavate basins, position first steel reinforcement layer, install outer forms. Days 4 to 8, pour concrete in 3 to 4 foot layers, Add additional steel layers as concrete rose. Install internal forms. Days 9 to 12. Allow curing. Remove forms carefully. Inspect for defects. Repair problems. Install ballast valves and hatches. Day 13. Flood basins slowly. Float completed caisson off foundation. Tow to holding area. This cycle maintained mechanical precision across all sites, though achieving consistency required solving hundreds of problems threatening delays. Supply logistics represented a massive undertaking. 400,000 tons Portland cement from Medway and Yorkshire Cement Works, shipped in 100-pound bags requiring dry storage. 1.2 million tons aggregate from Somerset, Yorkshire, and Scotland quarries, meeting precise specifications for size and cleanliness. 150,000 tons steel reinforcement bar from Sheffield and Birmingham mills. Seawater for mixing, pumped directly from adjacent harbors. Chemical admixtures from chemical plants, carefully measured during mixing. The British rail network absorbed additional 1,500 freight cars daily for Mulberry materials during peak production. Cement alone required 50 train loads daily, each train 30 hopper cars carrying 20 tons each, totaling 600 tons per train, 30,000 tons daily system-wide. The Ministry of Transport assigned dedicated freight trains running on priority schedules, superseding most civilian and some military traffic. Steel fabrication for whale pontoons occurred at shipyards across Britain. Harland and Wolff in Belfast produced 45 complete sections, each 1,600 feet long, requiring 8,000 tons steel plate rolled to precise thickness, 250 tons steel pipe for spud legs, 40 tons specialized steel for universal joints, 15,000 pounds welding rod consumed by welders working around the clock. Welders represented a training triumph. Pre-war Britain had 5,000 certified welders. Mulberry required 2,000 working simultaneously. The Ministry of Labor established crash training programs, recruiting women with no industrial experience and training them in 6 weeks on specific welds required for Mulberry components. Margaret Thompson, 19-year-old former textile worker from Manchester, trained November 1943, worked on whale pontoons at Harland and Wolff through May 1944. I had never seen welding equipment before training. They showed us how to strike an arc, maintain distance, move at right speed. After 2 weeks' practice, they put us on production. We welded steel plates making pontoon hulls. The welds had to be perfect because soldiers' lives depended on it. I inspected my own work more carefully than any supervisor. Quality control was rigorous and non-negotiable. Every critical weld was X-rayed to detect internal defects. Any weld showing cracks, voids, or incomplete penetration was ground out and re-welded. Early production rejection rates ran 15%, but by January 1944, experienced crews produced welds with rejection rates below 2%. By March 1944, Phoenix production ran at peak efficiency, 1 caisson every 2.5 days across all sites. Whale sections, 3 1,600-foot sections weekly. Total materials, 31,000 tons structural steel, 600,000 tons concrete, 120 miles steel cable, 15,000 tons chain, 2,000 concrete anchors at 5 tons each, 93 ships selected for scuttling. Economic cost was staggering. At 40 million pounds, $440 million, Mulberry consumed resources equivalent to 10 destroyers, 4,000 bombers, or 15,000 fighters. But without artificial harbors, Operation Overlord would fail. The production represented democracy's answer to totalitarian warfare. Free people voluntarily cooperating toward a common purpose, achieving what coercive systems could not imagine. The women welding steel, the workers pouring concrete, the engineers calculating stresses. These were the people who won the war as surely as any soldier on the beaches. June 6, 1944, D-Day, 1400 hours. While Allied troops stormed Normandy beaches, the first Phoenix caissons began their journey across the Channel. The towing plan, developed over 6 months, addressed unprecedented challenges. 146 caissons towed from construction sites to specific positions off Normandy, each 6,000-ton caisson requiring powerful tugs maintaining 3 to 5 knots. Routes crossing the busiest waters in the world, with thousands of vessels heading to Normandy. German U-boats, E-boats, and aircraft continuing to operate. Channel weather notoriously unpredictable, changing from calm to storm force within hours. The Royal Navy assembled 132 ocean-going tugs, 47 British Admiralty tugs with 2,000 horsepower engines designed for towing battleships, 33 Dutch tugs requisitioned from Dutch shipping companies operating from British ports after Netherlands occupation, 28 commercial tugs from British shipping lines pressed into military service, 24 American Moran Company tugs sent to Britain specifically for mulberry towing. Each tug was assigned a specific caisson and precise schedule coordinated to the hour. The first Phoenix departed Selsey afternoon, June 6th, at 14:30, towed by HMS Dexterous. The caisson, designated Phoenix B1, was 200 feet long, 60 feet wide, sat 15 feet deep in water, and displaced 5,800 tons. The tow cable was 800 feet of 3-inch diameter steel wire rope, capable of withstanding 150-ton tensions. Lieutenant Commander James Harrison. The caisson towed reasonably well at 4.5 knots in calm conditions. Steering required constant attention, as massive surface area caught even light winds. Crossing shipping lanes required extreme vigilance. We were towing a structure larger than most merchant ships, moving at half convoy speed, unable to maneuver quickly. Several times we signaled approaching vessels to alter course. The crossing took 19 hours, arriving off Arromanches at 9:30 June 7th. Towing continued 3 weeks, with caissons departing daily as completed. By June 12th, 32 Phoenix caissons had successfully reached Normandy, but there were losses. June 8th, Phoenix A7 broke loose during squall, drifted 6 hours, ran aground on sandbar 3 miles east of intended position. Total loss. June 10th, Phoenix B12 partially flooded when crack opened in concrete hull during towing. Tug crew, realizing caisson sinking, deliberately grounded it in shallow water off Isle of Wight, later salvaged, repaired with emergency concrete patches, successfully towed to Normandy, June 18th. June 13th, German E-boats from Cherbourg attacked convoy of 3 caissons at midnight. Destroyers HMS Tartar and HMS Ashanti drove off E-boats with gunfire before torpedo launch. Subsequently, all caisson towing got destroyer escorts. Whale pontoon sections presented different challenges. Each complete section was 1,600 feet long, consisting of 20 connected pontoons, flexing like a massive steel snake moving through water. Sections were towed by 2 tugs working in tandem, one front, one rear, to prevent jackknifing in turns. Lieutenant Harold Benson, commanding Tug Warden, towing whale section W7. Towing a whale section was unlike anything else. The structure flexed continuously as waves passed under it, undulating like a sea serpent. In turns, the rear half swung wide, creating tremendous strain on towing cable. We learned to make very gradual course changes. The crossing took 22 hours at 3.5 knots. By June 18th, 12 days after D-Day, majority of components reached Normandy. 118 Phoenix caissons, 28 lost or damaged beyond repair, 210 whale pontoon sections, 73 blockships, obsolete merchant vessels deliberately selected for scuttling, thousands of tons additional components, anchors, cables, pierheads, connecting spans. Assembly of Mulberry Harbor off Normandy, beginning June 7th, represented an engineering feat performed under conditions impossible to simulate in testing. Engineers worked in water depths 20 to 40 feet depending on tide, currents running 3 to 4 knots during tidal changes, sporadic German artillery fire from batteries inland, weather changing hourly, coordinating hundreds of vessels while combat operations continued on beaches. Phoenix positioning used celestial navigation, shore-based theodolites, and trigonometric calculations. Royal Navy survey teams established theodolite stations on cliffs overlooking Arromanches, June 7th. Lieutenant Commander Hugh Edwards. We established two stations 2,000 yards apart. By measuring angles from both to a target caisson, we calculated exact position using triangulation. We directed tugs by radio, telling them forward, back, left, right, in 10-yard increments until precisely on station. Process took 2 hours per caisson, longer if currents strong or winds made holding position difficult. Once positioned, caissons were deliberately sunk by flooding internal compartments in calculated sequences. The flooding procedure. First, open valves in 4 corner compartments, allowing water to enter slowly and evenly, settling the caisson level. Second, after corners 50% flooded, open central compartments. Third, monitor sinking rate using measuring poles, ensuring descent at 2 feet per minute. Fourth, when bottom 5 feet from seabed, close all valves temporarily and check position final time. Fifth, if position correct, open all valves fully, allowing caisson to settle onto bottom in approximately 3 minutes. Entire sequence took 45 to 60 minutes per caisson. Any error could cause caisson to tip, settle at angle, or drift off position during final descent. Divers descended to verify caissons settled properly. They worked in dangerous conditions. Water visibility often less than 3 feet due to silt. Strong currents during tidal changes. Cold water temperatures rarely above 55 degrees Fahrenheit, requiring diver rotation every 30 minutes to prevent hypothermia. Constant risk of being struck by debris, cables, or vessels. Petty Officer Samuel Wright, Royal Navy diver. We'd descend a weighted line attached to the caisson, carrying measuring rod and compass. Once on bottom, we'd feel our way around the base, checking it was level and properly seated on seabed. We couldn't see more than a few feet in murky water, everything done by touch. We'd measure gap between caisson bottom and seabed at multiple points, making sure it wasn't tilted. If we found gap larger than 6 inches, we'd report to surface, and they'd pump more ballast water into that side. Every dive felt like working blind in a storm. By June 12th, first breakwater section complete. 23 Phoenix caissons in 1,200 yard line, reducing wave heights inside by 60 to 70%. Outside the breakwater, 4 to 5 foot waves made landing craft operations difficult. Inside protected area, wave heights dropped to 1 to 2 feet, allowing landing craft to approach piers and unload cargo with relative ease. Whale floating roadways installed next. Installation crews worked from small boats, using hand tools to align universal joints, while sections rose and fell with tides and shifted with currents. Each connection took 20 minutes to complete, and a single 1,600-foot section required 19 connections. Thomas Mackenzie, rigger from Glasgow. We'd positioned 2 pontoon sections next to each other, close enough that joint mechanisms could engage, then manually align the 300-pound joint. Trick was timing with wave action. Pontoons constantly moving up-down 2 to 3 feet. Had to catch them when level, align joint, get pinned through before they moved out of alignment. Miss timing, lose a finger when those heavy steel components crashed together. By June 14th, Lieutenant Colonel David Strangeways, an American Army engineer, was among the first to drive across a completed whale roadway. I drove a Jeep from an LST moored at the pier head, down the floating roadway, all the way to the beach, approximately 800 yards. The roadway was 40 feet wide, plenty for two-way traffic. It rose and fell gently with waves, but no worse than a road with gentle hills. The surface was steel deck plate with raised ribs for traction. My Jeep's tires gripped it securely. Driving across it, you could look down and see water on both sides, waves lapping at pontoon edges. It was surreal. driving across the ocean on a steel road that didn't exist 2 weeks ago. The pierheads where ships would moor represented the most complex components. Each pierhead was essentially a large floating platform, 200 feet long and 60 feet wide, with multiple levels to accommodate different tide states. The pierheads rode on massive steel columns, called spuds, that were 90 feet tall and 6 feet in diameter. These giant spuds slid through guides in the pierhead structure, allowing the pierhead to rise and fall with tides while the spuds remained planted on the seabed. The pierheads could accommodate Liberty ships, LSTs, and smaller vessels simultaneously, with cargo cranes mounted on platforms to unload supplies directly onto trucks waiting on floating roadways. By June 16th, Mulberry B had 4 complete pierheads operational, capable of handling 16 ships simultaneously. Cargo capacity reached 5,000 tons per day and was increasing as additional components were installed and procedures refined. American engineers working on Mulberry A at Omaha Beach reported similar progress. Their harbor was handling 4,000 tons per day by June 17th, with capacity projected to reach 7,000 tons by June 25th. The 2 artificial harbors combined were on track to exceed 15,000 tons daily capacity, more than enough to sustain Allied forces through the critical buildup phase. Then, on June 19th, nature intervened with a demonstration of power that no amount of engineering could completely overcome. At 4 hours on June 19th, 1944, meteorologists at Allied headquarters in Portsmouth detected a weather system developing over the Atlantic, showing all characteristics of a major storm. The forecast transmitted to all commands in Normandy at 6 a.m. warned of gale-force winds reaching 40 to 50 miles per hour, waves building to 8 feet or higher, and conditions persisting at least 48 hours. It was the worst channel storm in 40 years, arriving at the worst possible moment, just as the Mulberry harbors were entering full operation. The storm struck the Normandy coast at 8 hours June 19th, with winds that quickly exceeded forecast predictions. By noon, winds sustained at 45 miles per hour, with gusts reaching 60. Wave heights outside breakwaters reached 10 feet, and even inside protected areas, waves of 5 to 6 feet battered the whale roadways and pierheads. The Phoenix breakwaters performed as engineered. Waves broke against the concrete caissons, dissipating energy and reducing wave heights on the leeward side. But the floating components faced conditions at the absolute limit of their design specifications. At Mulberry A, the American harbor at Omaha Beach, problems began appearing within hours of the storm's onset. Several whale pontoon sections, anchored by spud legs that had not fully penetrated hard sand substrate, began walking across the seabed as wave action rocked the pontoons. The walking motion gradually pulled the legs loose, and by 1400 hours June 19th, a 480-foot section of whale roadway broke free from its anchors. The freed section, driven by wind and waves, crashed into an adjacent section still anchored, and the collision severed connecting joints. Both sections tore loose and began drifting. American engineers attempted to recapture the drifting sections using tugs, but storm conditions made maneuvering impossible. By 1800 hours, 6 separate whale sections had broken loose at Mulberry A, creating a cascading failure as each drifting section crashed into and damaged others. Engineers made the decision to evacuate all personnel from floating structures and ride out the storm, hoping the breakwaters would hold even if internal components were damaged. Through the night of June 19th to 20th, the storm intensified. Winds reached sustained speeds of 50 miles per hour, with gusts to 65. Wave heights outside breakwaters peaked at 12 feet, the highest waves recorded in the English Channel during June in over a century. Inside the breakwaters, even with wave energy reduced by 70%, wave heights still reached 6 feet, battering floating structures with relentless force. At Mulberry B, the British harbor at Arromanches, engineers watched with mounting concern as the storm tested every component. The Phoenix caissons, weighing 6,000 tons each and firmly settled on the seabed, absorbed wave impacts without movement. The whale roadways flexed and twisted, but remained anchored, the spud legs holding firm in the softer substrate that characterized the Arromanches seabed. The universal joints connecting pontoon sections performed exactly as designed, allowing the roadways to flex with wave action rather than resisting rigidly and breaking. But one section of the harbor showed signs of dangerous stress. The eastern breakwater, where several Phoenix caissons had been positioned in deeper water to extend the protected area, was taking the full force of the storm. One caisson, Phoenix B-47, had settled, slightly tilted due to an irregular seabed. Nothing serious under normal conditions, but under storm loading, the tilt created uneven stress distribution. At 300 hours, June 20th, Phoenix B-47 cracked. The crack, starting at a point where the tilt had concentrated stress, propagated through the concrete in seconds. Seawater flooded through the crack, and the caisson began to settle unevenly, tilting further. Within 30 minutes, Phoenix B-47 had tilted 15 degrees from vertical, creating a gap in the breakwater that allowed waves to surge through into the protected area. British engineers monitoring from the cliffs made an emergency decision: deliberately sink a blockship in the gap to restore breakwater protection. The blockship, Durban, an obsolete freighter held in reserve for exactly such emergencies, was towed into position at 8 o'clock hours, June 20th, despite storm conditions. The tug crew, displaying seamanship that would later be recognized with commendations, positioned Durban directly in the gap, then opened her seacocks to scuttle her in place. Durban settled to the bottom within 20 minutes, her superstructure remaining above water and partially blocking the gap. The makeshift repair worked. Wave energy penetrating through the gap dropped by 50%, reducing stress on internal harbor components. The storm continued through June 20th and into June 21st before finally moderating. By the morning of June 22nd, winds had dropped to 25 miles per hour and wave heights were declining. Engineers ventured onto the floating structures to assess damage. At Mulberry A, the damage was catastrophic. The American harbor had been effectively destroyed. 28 whale pontoon sections damaged beyond field repair. 8 Phoenix caissons shifted off position or cracked. All 4 pierheads damaged. 2 capsized completely. Estimated 6 to 8 weeks required for repairs using replacement components that didn't exist. American commanders made the decision on June 23rd to abandon Mulberry A and salvage usable components to reinforce Mulberry B. The resources that had gone into building the American harbor, the concrete, steel, labor, and months of preparation, were written off as a total loss. At Mulberry B, the damage assessment told a dramatically different story. The British harbor had survived. 118 Phoenix caissons remained in position, with only 3 damaged, including B-47. 187 of 210 whale pontoon sections intact and functional. All pierheads damaged but repairable. Estimated 3 to 5 days required to restore full operational capability. The survival of Mulberry B, while Mulberry A was destroyed, revealed critical differences. The Arromanches location had softer seabed substrate that allowed spud legs to penetrate deeply and hold firmly. The Omaha Beach location had harder sand that resisted spud penetration, leaving anchoring legs partially loose. British engineers had been more conservative in positioning Phoenix caissons, placing them in shallower water where wave forces were reduced. American engineers had positioned caissons more aggressively in deeper water to maximize the protected area. British whale sections had been connected with additional safety cables as backup to the universal joints. American sections relied solely on the joints, which proved vulnerable to extreme storm conditions. By June 26th, Mulberry B was operational again, handling 5,500 tons of cargo daily. By July 1st, capacity had been restored to 7,000 tons daily, with the addition of salvaged components from Mulberry A. The harbor that German strategic planning had assumed could not exist had survived the worst channel storm in 4 decades and was now outperforming pre-war commercial ports. By July 1944, Mulberry B had settled into routine operations that demonstrated the true strategic value of the artificial port. The daily statistics were staggering and grew more impressive as procedures were refined. Daily cargo volume averaged 7,000 tons in July, increasing to 9,000 tons by August. Peak daily throughput reached 11,400 tons on August 16, 1944, exceeding any single day's cargo handling at the Port of Dover in peacetime. Vehicle throughput averaged 1,500 vehicles daily: trucks, jeeps, tanks, artillery pieces, all driven from ships directly to shore via the floating roadways. Personnel throughput exceeded 10,000 men per day during peak periods as fresh divisions arrived to replace casualties and reinforce the front lines. The cumulative statistics, compiled by Allied logistics officers, revealed the true scale of what had been accomplished. From June 19, 1944, when Mulberry B achieved initial operational capability, through November 19, 1944, when the harbor was officially closed after Antwerp's port facilities became available, Mulberry B handled 628,000 tons of supplies, ammunition, fuel, and equipment, 39,000 vehicles of all types, 220,000 personnel. These figures represented approximately 40% of all supplies landed over the British-Canadian beaches during that period, with the remaining 60% coming from direct beach landings during favorable tides and weather. The cargo volume handled through Mulberry B exceeded the tonnage that passed through Cherbourg in the same period, despite Cherbourg being a permanent port with facilities developed over centuries. American engineers had finally captured Cherbourg on June 26, 1944, after 3 weeks of fighting that cost 3,000 American casualties. German defenders, following Hitler's orders to destroy everything of value, had systematically demolished the port facilities before surrendering. The destruction was thorough and methodical. All cranes blown up, their twisted steel wreckage dumped into the harbor. Dock facilities mined and collapsed. Harbor waters filled with scuttled ships, deliberately sunk to block approaches. Underwater obstacles, mines, and booby traps left throughout the harbor area to delay clearance operations. American engineers worked around the clock for 3 months to restore Cherbourg to partial operation. The port didn't reach its full pre-war capacity until November 1944, 5 months after capture. During those critical months, Mulberry B, built from scratch in less than a year, towed across the channel in pieces, and assembled under fire, outperformed a permanent port that had existed since Roman times. The strategic implications were profound and had been immediately recognized by German commanders who understood logistics. General der Panzertruppen, Leo Geyer von Schweppenberg, commanding Panzer Group West, submitted a situation report to OKW on July 15, 1944. The Allied artificial harbor at Arromanches is handling cargo volumes that exceed our most pessimistic intelligence estimates. They are landing more supplies in 1 day than we can transport to the front in 3 days, despite our interior lines of communication. They have more fuel available in Normandy than we have in all of France. They are replacing equipment losses faster than we can inflict them. The logistical advantage they have gained through this artificial harbor makes eventual defeat certain unless we can destroy it. The recommendation was forwarded to Hitler's headquarters, but was effectively ignored. German artillery within range of Arromanches had been suppressed by Allied naval gunfire and fighter-bomber attacks. The Luftwaffe lacked the aircraft, fuel, and pilots to mount sustained attacks on the harbor. German E-boats and submarines attempting to approach Arromanches were hunted by Allied destroyers and aircraft with such effectiveness that attacks became suicide missions. The artificial harbor was effectively invulnerable to German attack, protected by overwhelming Allied air and naval superiority. The contrast between Allied and German logistics by July 1944 had become so stark that it defied rational military analysis. German forces in Normandy faced supply crises that rendered entire divisions' combat ineffective, fuel shortages that immobilized panzer divisions, leaving tanks sitting in assembly areas while Allied forces maneuvered freely. Ammunition rationing that limited artillery to 3 rounds per gun per day in some sectors, while Allied artillery fired 30,000 rounds daily. Food shortages that reduced German rations to 1,500 calories per day, barely above starvation level, while American soldiers received 4,000 calories daily, plus supplemental rations. Medical supply shortages that left German field hospitals without anesthetics, antibiotics, or basic surgical supplies. These shortages weren't caused by lack of production. German factories were still manufacturing ammunition, fuel, and supplies in substantial quantities. The problem was transportation. Allied air superiority had made daylight movement impossible. German supply convoys moved only at night, traveling at reduced speeds, vulnerable to partisan attacks, forced to use secondary roads because main highways were targeted by fighter bombers. The average German supply convoy in July 1944 took 4 to 5 nights to move supplies from railheads, 100 miles behind the front to forward units, assuming the convoy wasn't destroyed en route. Allied supplies moved from Mulberry Harbor to frontline units, a similar distance, in 8 to 12 hours in broad daylight, on roads crowded with truck convoys that faced no air threat whatsoever. The Red Ball Express, the famous truck convoy system that would become legendary for sustaining Patton's advance across France, had its genesis in the logistics success of Mulberry Harbor. The Express began operations on August 25, 1944, using 6,000 trucks driven primarily by African-American soldiers from the Quartermaster Corps. The trucks ran in continuous convoys on dedicated routes from supply dumps near the beaches to forward areas, delivering 12,500 tons of supplies daily at peak operations. Corporal James Anderson, a driver with the 3383 Quartermaster Truck Company, described the Red Ball Express operations in a 1989 interview. "We drive our trucks from supply dumps near Paris back to the beach areas, load up with ammunition, fuel, rations, whatever the forward units needed, then drive back. Round trip was maybe 600 miles. Took 2 days if everything went smoothly. We'd pass German prisoners being marched to the rear, and they'd stare at our convoys like they couldn't believe what they were seeing. Hundreds of trucks, all full of supplies, driving in daylight, without any concern for air attack. I think that's when they realized they'd lost the war, when they saw how much stuff we had and how easily we could move it around." The contrast between the Red Ball Express and German logistics capabilities symbolized the fundamental difference between American and German approaches to warfare. The Americans had solved the logistics problem through industrial production, building enough trucks that vehicle shortages never occurred, producing enough fuel that consumption was never rationed, manufacturing enough ammunition that forward units could fire without restriction. The Germans attempted to solve logistics through tactical efficiency, trying to win battles quickly before supplies ran out, rationing resources to maximize their effectiveness, relying on superior training and doctrine to overcome material shortages. By mid-1944, the German approach had failed completely. General Oberst Alfred Jodl, chief of Wehrmacht operations staff, met with Hitler on October 1, 1944, to present an assessment of German military capability. According to records of the meeting preserved in Wehrmacht files, Jodl's briefing was blunt. "Mein Führer, the military situation is untenable and will only worsen. The Allies are landing 30,000 tons of supplies daily through their artificial harbors and beaches. Our intelligence indicates they have 90 days of supplies stockpiled in France. Fuel, ammunition, food, spare parts. They can sustain offensive operations indefinitely. By contrast, our forces have perhaps 15 days of supplies at current consumption rates, and replacement supplies are not reaching the front due to Allied air interdiction of our rail network. We are losing the war through logistics." Hitler's response, documented in the meeting notes, revealed his complete disconnect from reality. The Allies are overextended. Their artificial harbors are temporary expedients that cannot sustain operations through winter. When storms destroy these harbors, their logistics will collapse, and we will counterattack. The German soldiers' superior fighting spirit will overcome material disadvantages. This assessment would prove catastrophically wrong on every point. The German military's evolving understanding of the Mulberry Harbors, from initial disbelief to grudging acceptance to horrified recognition of what they represented, provides crucial insight into how the Third Reich's ideology and strategic assumptions led to catastrophic miscalculation. The first German intelligence reports mentioning unusual Allied activity off the Normandy coast appeared on June 8, 1944. Luftwaffe reconnaissance aircraft photographed what pilots described as large rectangular objects being towed toward the coast. Intelligence officers at Luftwaffe headquarters in Paris classified the objects as probably large fuel barges or ammunition lighters. This assessment, fundamentally wrong but understandable given the unprecedented nature of what was actually occurring, shaped German strategic thinking for crucial weeks. If the Allies were dependent on floating supply barges, vulnerable to storm and attack, then denying them port access remained a viable defensive strategy. By June 15th, reconnaissance flights obtained clearer photographs showing Phoenix caissons being positioned and whale roadway installation beginning. These photographs reached Army Group B headquarters, where intelligence officers examined them with growing confusion. Major Siegfried Westphal, an intelligence analyst on Rommel's staff, later described his reaction in post-war interviews. "We saw these concrete structures, enormous boxes, being positioned in lines extending from shore. We saw what appeared to be floating roads, steel platforms stretching from these concrete boxes toward the beaches. Initially, we thought we were looking at temporary structures for beach supply operations. Then someone calculated the size of these concrete boxes from the photograph scale. They were 60 meters long. No one builds 60-meter concrete boxes for temporary beach operations. That's when we began to realize we might be seeing something unprecedented." Westphal prepared a detailed analysis forwarded to Field Marshal von Rundstedt's headquarters on June 17th. His conclusion was carefully worded. Allied forces are constructing what appears to be an artificial harbor using prefabricated components. If this assessment is correct, the scale and sophistication suggest industrial capabilities far exceeding our previous intelligence estimates. The report generated heated debate at German headquarters. Many officers simply refused to believe the Allies could build functional harbors from prefabricated components. The concept violated everything they understood about port construction and military logistics. But reconnaissance photographs didn't lie, and by late June, the evidence was overwhelming. Oberst von der Heide's detailed reconnaissance report, submitted December 20, 1944, represented the first comprehensive German assessment based on direct observation. His report, classified secret and distributed to all major German commands, provided specifications that shocked readers. The artificial harbor at Arromanches extends 3,000 meters from shore. It is protected by massive concrete breakwaters that reduce wave heights by approximately 70%. Inside the protected area, floating roadways connect to multiple pierheads capable of accommodating ocean-going vessels. The cargo handling capacity is estimated at 7,000 to 9,000 tons daily, equivalent to a major commercial port. The harbor has been operational since mid-June and has handled an estimated 600,000 tons of cargo to date. Von der Heide's report concluded with an assessment that many German officers found defeatist, but that proved brutally accurate. "We are not losing this war through lack of courage, tactical skill, or fighting spirit. We are losing because the Allied nations, particularly the United States, possess industrial and economic resources that dwarf our own. The artificial harbor is merely one visible manifestation of this disparity. For every ton of supplies we can transport to our forces, the Allies can transport 10 tons to theirs. These are not ratios that tactics can overcome. These are mathematical certainties that lead inevitably to defeat." Hitler's response to intelligence reports about the Mulberry Harbors revealed his complete inability to accept reality when it contradicted his ideological worldview. In a meeting with military commanders on January 10, 1945, documented in Wehrmacht records, Hitler dismissed the significance. The artificial harbors demonstrate Allied material abundance, but also reveal their weakness. They depend entirely on technology and industry because they lack the fighting spirit of German soldiers. When weather destroys these harbors, when U-boats sink their supply ships, their logistics will collapse. Victory comes not to those with the most supplies, but to those with the greatest will. This fantasy, that willpower could overcome material reality, that spirit could triumph over mathematics, characterized Nazi thinking throughout the war and ensured Germany would fight until total destruction. Mulberry B continued operations through October-November 1944. October statistics: 254,000 tons cargo, 11,200 vehicles, 87,000 personnel. Average 8,200 tons daily, peaks exceeding 10,000 tons. 96% operational availability. These figures exceeded Cherbourg, partially restored after 4 months intensive repairs. The artificial harbor, built in months and assembled in days, outperformed a permanent port existing for centuries. By November 1944, the strategic situation had shifted dramatically. Allied forces had broken out of Normandy, liberated Paris, and were advancing toward Germany's borders. The port of Antwerp in Belgium had been captured, and by November, engineers had cleared the Scheldt estuary, making Antwerp's massive port facilities available. Antwerp could handle 40,000 tons daily, 4 times Mulberry's capacity, and was 200 miles closer to advancing front lines. November 19, 1944. Mulberry B officially decommissioned. Decision purely practical. Antwerp's capacity made the artificial harbor redundant. Salvageable components recovered. Steel pontoons towed to Antwerp, repurposed as pier extensions. Pierhead cranes dismantled and moved to other ports. Anchors, chains, hardware sent to supply depots. Phoenix caissons, too massive to recover practically, left in place. Some later demolished to prevent navigation hazards. Others remain today, visible at low tide, monuments to engineering achievement. In 153 days operation, Mulberry B handled 628,000 tons supplies, enough for 125,605-ton trucks, 39,000 vehicles, 25% of all vehicles landed over British beaches, 220,000 personnel, countless intangibles, medical supplies, saving lives, ammunition enabling offensives, fuel keeping armies mobile, food sustaining soldiers through combat. Final cost, £40.2 million, $442 million, slightly over budget. Cost per ton cargo, £64, $704. By comparison, constructing permanent port facilities with equivalent capacity, estimated £120 million, taking 3 to 4 years. Mulberry provided equivalent capacity for 1/3 the cost in 1/10 the time. The artificial harbors represented something more profound than engineering achievement. They embodied the fundamental difference between democratic and totalitarian approaches to warfare. The Nazi regime had mobilized Germany's industrial capacity through coercion, slave labor, and ideological fervor, achieving impressive production volumes but ultimately constrained by rigid thinking and refusal to acknowledge limitations. American industry mobilized through different mechanism. Collective recognition that the war demanded impossible feats, followed by pragmatic calculation of how to achieve them. Impossible was not an excuse, but an engineering challenge to be systematically dismantled through planning, resources, and relentless execution. The women who welded steel for floating roadways, the African-American workers who poured concrete for Phoenix caissons, the British engineers who calculated tide tables and ballast sequences. These were the people who won the war as surely as any soldier on the beaches. They proved that a democratic society, when mobilized toward common purpose, could achieve feats that totalitarian regimes could not imagine, let alone match. The Mulberry Harbors cost $440 million, required 600,000 tons of material, and demanded 20,000 workers laboring for a year. Nazi Germany, with its vaunted industrial efficiency and total war economy, could not have built them, not because German engineers lacked skill, but because the project required a level of voluntary cooperation, innovative thinking, and resource allocation that a coercive system could not sustain. The ruins of Mulberry B still stand at Arromanches today. Massive concrete caissons visible at low tide, rusting steel visible in the sand. Monuments to engineering ambition and systematic execution. French schoolchildren visit on field trips, learning about the harbor that helped liberate their country. British veterans return to trace paths their trucks drove down floating roadways. American tourists photograph the concrete remains and struggle to comprehend the scale of achievement in just 12 days in June 1944. The harbor, German officers thought impossible, that Nazi propaganda dismissed as Allied fantasy, that defied every principle of traditional military logistics, processed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies in 10 months of operation. It was built by workers who had never poured concrete before, welded by women who had never held torches before, designed by engineers solving problems never attempted before. And it worked. It worked because free people, voluntarily cooperating toward common purpose, can achieve what totalitarian systems cannot imagine. It worked because American industrial capacity, mobilized by democratic consensus rather than dictatorial coercion, could manufacture miracles as easily as it manufactured jeeps. The artificial harbors weren't just engineering achievements. They were democracy's answer to totalitarianism, spoken in concrete and steel, assembled under fire, and functioning while skeptics insisted they couldn't exist. They were proof that free societies, when threatened, can mobilize capabilities that authoritarian regimes cannot match. They were the physical manifestation of the American industrial spirit. If you need something that doesn't exist, you don't complain about its absence. You build it, ship it, and make it work. The German officers who first witnessed the Mulberry Harbors thought they were seeing deception, propaganda, impossible fantasy. They were wrong. They were witnessing the future of warfare, where industrial capacity determines outcomes more surely than tactical brilliance or ideological fervor. They were witnessing the moment when systematic American problem-solving, applied with overwhelming industrial force, made traditional military wisdom obsolete. They were witnessing their own defeat, delivered not by better generals or braver soldiers, but by a nation that could build harbors where none existed and make the impossible routine. The mathematics were clear, inevitable, and final. America could build artificial harbors faster than Germany could destroy real ones. That single fact, more than any battle or campaign, explains why the Third Reich fell and democracy prevailed. The Mulberry Harbors were not just logistics, they were destiny, manufactured in segments, towed across the channel, and assembled into the instrument of totalitarianism's defeat.